Hello viewers, welcome back to the course on matrix computation and application. So, in the previous lecture we have started with the linear transformations. So, now in this lecture we will continue with that one. So, in the previous lecture we have started with the linear transformation, that suppose I have a vector space U and another vector space V. So, I define a transformation T from U to V, and this transformation T is a transformation from U to V, and if it satisfies the condition that T of U1 plus U2 is equal to T of U1 plus T of U2, and T of alpha U, that becomes alpha Tu, where U1 and U2 belongs to U. So, it is true for all U and U2, and this is also true for all U belongs to U and alpha belongs to the scalar field F. So, this transformation is called the linear transformation if it satisfies these conditions. Now, we want to use some properties, or maybe I call it theorem, that let I have a transformation from U to V. So, suppose be a linear transformation if so, then first one I want to show that T of the 0 element in the U, that will map to 0 element in the V. The second one is T of minus U, that will be equal to minus of Tu, and the third one is that if I take the transformation of the linear combination. So, suppose I have a alpha 1 U1 plus alpha 2 U2 plus alpha n UN, that will be equal to alpha 1 T of U1 plus alpha T of U2 up to alpha n T of UN. So, these are the three results about the transformation. Now, we can prove very easily all this one. So, proof. So, the first one is that now in this case you can check that this I have written OV means this is the 0 element of vector space V, and this is the 0 element, or maybe I can write that 0 element of vector space U. So, now from here we know that, so we know that for any U belongs to U, if I put U plus 0 of U, that equal to U. Now, if I take the transformation U plus 0 of U, then by the property of linear transformation it will be equal to T of U plus T of 0 U, and now this can be written as, now since U plus 0 of U, that is equal to U, which implies that, so now from this one left hand side will become T of u plus OU, that becomes T of U. So, now I can write from here that T of U plus OU I can write. So, maybe I can give this as a equation number 1. Now, from equation 1 we can write T of U on the left hand side, and right side is already TU, this one. And now, from here I can write my T of OU, that is equal to T of U minus T of U. And now, T of U is in the V and minus TU is also in the V, that is just the inverse, additive inverse of TU. So, then it will be equal to 0 of V. So, from here we can say that T of 0 of U, that maps to 0 in V, this one. Okay, so, from here the thing is that suppose we have a transformation from, maybe I will call it V3 to maybe V2, then it is understood from here that T of 0 0 0, because 0 0 0 is the 0 of V3. So, this element you can call it 0 of V3, and this will be equal to 0 0, and this is 0 in V2. So, by this one, this is always true, that 0 element of the space U will map into the 0 element in the space V. So, this is the first one. So, the second one is, now we know that T of minus U. So, I want to prove this one. So, let us say that I will take T of alpha U, that is alpha TU, and alpha is coming from the field. So, in the field, now if I choose alpha is equal to minus 1, because 1 is there in the field. So, its additive inverse minus will definitely will be in the field. So, in the given field. So, from here we can have that T of minus U, then it can be written as T of U, and this is true for all element of U. And the third one is, we can prove. So, we can prove as, like I have some linear combination. So, what I am going to do is that, so let we have a U1, U2, UN all belongs to U. Then the linear combination of U1, U2, UN will be like alpha 1 U1, alpha 2 U2, and alpha n UN, and this is also belongs to U, that we already know. So, now what I do is that, so this is the one. So, I can write this as T of alpha 1 U1, alpha 2 U2, alpha n UN. So, this one I can write, I can choose this part as some U, because this is also linear combination of U2, U2 up to UN, and from here I can write this as a T of alpha 1 U1 plus U, and this one is, I can write from the property of the linear transformation, this can be written as alpha 1 T of U1 plus T of U, and then T of U can further be written in this form, and from here I can write now TU can further be written as T of u will be equal to T of alpha 2 u 2 up to alpha n u n. So, I can write this as again alpha 2 T of u 2 plus the remaining the next part, this one I can call it maybe u dash. So, it will be equal to T of u dash, and similarly I can go and from here going using the same argument we can write that T of alpha 1 u 1 plus alpha 2 u 2 up to alpha n u n, that will be equal to alpha 1 T of u 1 plus alpha T 2 T of u 2 and alpha n T of u n. So, the same alphas are working here in here also and here also. So, this is the linear combination. So, this is a linear combination in U, and you can check from here that this is a linear combination in V. So, alphas are the same and these things are different. So, that is the, it means that the linear transformation of the linear combination U, that is equal to the linear combination in V, and the alpha is the coordinates will be same. So, this thing is we can prove from here. Now, so after doing this one, so now what is we need to do is that, so the next thing is that question is how to write a linear transformation, say from vector space U to the vector space V. So, the question is that how I can write the linear transformation. Now, because I want to find the linear transformation T from U to V, this one I want to find. It means, and my T is that for any U belongs to U, T of U should belongs to V. So, it means for finding the linear transformation, I need to find the value of that transformation for each U belongs to U, and it means, and we already know that U is a vector space. So, if it is U is a vector space, it is going to have an infinite number of points. So, it is not possible for us to find the image of each member of the vector space U. So, how we can find the linear transformation from one vector space to another vector space? So, these things we need to find out. So, this is possible if we talk about the basis, because we know that suppose I have a vector space U and that is nth dimension, n dimensional. So, U is suppose n dimensional. Then suppose I have a basis U1, U2 up to Un. So, this set is the basis of vector space U. Now, from here we know that for any U belongs to U, I can write U as some linear combination alpha 1 maybe U1 plus alpha 2 U2 up to alpha n Un. And since this is a basis, so if it is a basis, then it is Li. So, from here we know that this alpha 1, alpha 2, alpha n are unique. So, I can find the system of equation, and that system of equation is going to have a unique solution, because U1, U2 un are linearly independent. So, this representation will be unique. Now, so it is any u, so u belongs to u. So, this is true for any u. Now, I can, if I am able to find the T of u, then we are done. So, T of u we can find out. So, how we can find out define the T of u? So, that we do with the theorem. So, let us write one important theorem, or the definition you can write. So, a linear transformation T is completely determined by its values on the elements or vectors of a basis. So, it is completely determined by its value on the elements or the vectors of a basis. So, basis of T basically, basis of u. So, how you will define that one? So, I can write that precisely if suppose I have a B is a set of vectors u1, u2 up to un. So, I am defining the linear transformation T. So, T maybe you can define from u to v. So, let I take the set B. So, is the basis is a basis for the vector space u. Now, there exist, now let there are vectors v1, v2 up to vn that belongs to the vector space V. Then there exists a unique linear transformation, there exists a unique linear transformation T from u to v such that T of ui is equal to vi, and this is true for all I 1, 2, 3 up to n. So, from here we can say that I have taken a basis of the vector space u, and suppose there exists some vectors v1, v2, vn, n number of vectors that belongs to v, then I can find a unique linear transformation from tu to tv from u to v as tui is equal to vi. It means from here you can see that we are able to find the image of each vector in the basis. So, if we are able to find the image of each element in the basis, then we are able to find the linear transformation. So, this things is, so this theorem is gives you that how we can find out the linear transformation. Now, so this proof is very simple, that now I have a basis B is equal to the basis u1, u2 up to un. So, this is the basis of vector space u, and suppose it is a basis, it means that the dimension of u is n, that we already know, It is a basis means it spans U and they are linearly independent. Now, for any U belongs to the space vector space U, I can write U as alpha 1 U1 plus alpha 2 U2 alpha n Un. So, first I define that how we can find out the linear transformation. So, I can write like this one. So, maybe I call it 1. Now, since U1 U2 Un are, so this is a basis or all are linearly independent, which implies that alpha 1 alpha 2 alpha n, this set of or coordinates. So, this is the coordinate vectors, and this vector I call it coordinate vector. So, this coordinate vector is unique, means this system is not going to have an infinite many solution, it is going to have a unique solution, because it is a linearly independent. So, I know that the rank will be equal to the n here. So, it will be the unique solution. So, now from here I can write, then now we define T of U is equal to alpha 1 V1 plus alpha 2 V2 alpha n Vn, and you know that V1, V2, V3 all are coming from the vector space V. So, these are this one. So, now we define a transformation T of U that is equal to alpha 1 V1 plus alpha 2 V2. So, I claim that this is a linear transformation. So, I call it maybe 2. So, I define this as a linear transformation. So, I am taking T of U is equal to alpha 1. So, alpha is are coming from here, and V1 is the vector we have taken from the vector space V. So, let us do this one. So, I need to check. So, we need to check. So, of course, its T is from U to V. So, what we need to check, first one is T is a linear transformation. So, this we need to check, and the second one is we need to check that T satisfies the condition T u I is equal to V I, because this is what we have shown here, that it can be determined if it has the image of each of the basis element of a basis of a vector space U. So, satisfy this condition, and the third one is that T is unique. So, it should be unique. So, these things we need to check. Now, the first one we can check that T is a linear transformation LT. So, this one we need to check. Now, for U I know that for any maybe I can take U dash. So, for any U dash belongs to U, we can write u dash is equal to, suppose it is coming beta 1 u 1 plus beta 2 u 2 and beta n u n, and this is true. So, this can be written as this one, and this representation is unique, that we know. Now, T of u plus u dash, let us see what is going to happen. So, this can be written as T of u, u is alpha 1 u 1 plus alpha 2 u 2 alpha n u n plus beta 1 u 1 plus beta 2 u 2 beta n u n. And since this belongs to the vector space, so I can write this as a alpha 1 plus beta 1 u 1, and I can write here alpha n plus beta n u n, and this can be written as, now these things we already seen that this is equal to alpha 1 plus beta 1 T of u 1 and alpha n plus beta n T of u n. And from here I can separately I can write like this one. So, it can be written as, I can write it as alpha 1 T of u 1 alpha n T of u n. So, I can write like this one plus beta 1 T of u 1 beta n T of u n, and this one is again, so I can write this as T of alpha 1 u 1 T of alpha n u n plus the same way I can write T of beta 1 u 1, because the linear transformation I have taken this one. So, T u is alpha 1 alpha 2 alpha n, where u have written like this one alpha 1 alpha 2 alpha n. So, I am taking T of u plus u, this is coming like this one, and this one I can write in this way from. So, this we have taken from the equation 2, this one using equation 2, and now I am doing this one as alpha 1 T u because that belongs to the vector space V. So, this one, and now I am going back from there. So, I can write this as a beta n T of beta n u n. So, here also I am taking the help of the equation number 2, because alpha 1 T u 1 and this alpha n T u n. So, I am writing in this way, and maybe from here I can write directly. So, after writing this one, because to show that it is equal to T u plus T v. So, from here I can write this one can be written as, so it is, if you see from here, then it is equal to T u plus T v, because I am writing here that alpha 1 v 1 plus alpha 2 v 2, some vector is there, and this is coming. So, T u 1 I am taking as a element from as a v 1, and this is I am taking as a v 2 or v n, and then we are putting this value here. So, this becomes T u plus T v. Similarly, we can define T of alpha some u, that can be easily written as alpha of T u. Now, and also, so it is a linear transformation. Also, now we have a T of u is equal to alpha 1 v 1, alpha 2 v 2, alpha n v n. So, this thing is there. Now, from here how we are writing like this one, I can show you that since u 1 T of u 1 can be written as, now what is going to happen here? Now, we are defining this as a T of u. So, this one I can write as T of, maybe I can write as a T of u 1 plus 0 u 2 0 u 3 0 u n. This one I can write like this, and this one I know that this is equal to T of u 1 plus 0 T of u 2, that we have already know, and this is equal to T of u n. Now, from here I can write this as, because this is a 0 element, so it will be T of u 1, and this, if you see from here, then this is same as v 1, because we have defined the linear transformation in this way, that T of u is equal to alpha 1 v 1, and this alpha, alpha 2, alpha n are coming from there. So, from here I can say that my alpha 1 is 1, alpha 2 is 0, and all alpha, these are the 0. So, from here it will, I will left only with alpha 1 v 1, and that will be equal to T u 1. So, it means that this is equal to v 1. So, the same concept will go similarly. We can show that T of u I is equal to v I, and this is true for all I from 1 to up to n. The same argument will work there. Similarly, I can define T of u 2. So, T of u 2 will be 0 u 1 plus u 2 plus all the other elements 0, and then from here it will be that T u 2 is equal to v 2. So, this one we can define like this from here. So, here we have defined this property, and then we got this value. Now, so this conditions is there that each of the basis elements should have a image in the vector space V, like this one, T u I is equal to V I. So, the third one is, so I want to show the third one is that the T is unique, means if I have a set of bases and have a set of element that is V 1, V 2, V n, then we can have a only unique linear transformation. So, T is unique means unique with respect to basis, that is u 1, u 2, u n, and the set V 1, V 2, V n, such that T of u I is equal to V I. So, that if you change any of the thing condition, then you will get another transformation that we need to show that it is unique. So, these things we can prove on contradiction, that let S is another linear transformation such that S of ui is equal to vi. So, this I am taking the another linear transformation, true for all I 1 2 up to n. So, this is I am taking. Now, from here I know that S of, so for any u, that will be S of, I know that u can be written as a alpha 1 u 1 plus alpha 2 u 2 alpha n u n. Now, this can be written as alpha 1 S of u 1 alpha n S of u n. Now, alpha S of u I is equal to v I. So, I can write this as a alpha 1 v 1 plus alpha 2 v 2 alpha n v n. This is what we have defined here. Now, if you see from here, then this is equal to T of u, and this is true for all u. So, which implies that S will be equal to T, because this is true for all u. Whatever we have done taken, that gives you that S u is equal to T u for all u. So, from here I can say that S is equal to T, and that gives you that T is unique. So, T will be unique. So, always we to define the linear transformation, we need a set of bases in the vector space U, and then we need some vectors in V, so that we can define a map like this one. So, suppose we have the knowledge of T u I is equal to V I, and based on this knowledge I can define the linear transformation like this one, and that linear transformation, that transformation will be linear transformation, and it will satisfy this condition, and it will be unique. So, that way we can define the linear transformation. So, today let me stop here today. So, in the today's lecture we have started that how we can define a transformation, linear transformation from a vector space U to a vector space V. So, in the next lecture we will perform some examples that how we can find out the linear transformation based on the given basis given to us for a given vector space U. So, thanks for watching, thanks very much.